Good morning, everyone. My name is Zuzanna Kowalczyk from the Gdańsk University of Technology. Today, I'd like to talk to you about counting sheep, but not really the kind that helps you sleep. I'm going to present a combinatorial approach for optimal distribution, specifically focusing on how we can use mixed integer linear programming to solve dispersion problems. Let's start with a scenario. Imagine we are in a meadow with 4 potential safe locations: a patch of grass, a forest, a pond, and a pub. However, there is a danger lurking: a wolf. As you can see, the wolf unfortunately keeps eating all the sheep, which leaves them very, very sad, until one of them has decided she had enough and she will do something about it. And so the goal isn't just to put the sheep anywhere, to any safe location, but to distribute them intelligently among these locations to ensure they are safe from the predator. To model this mathematically, we first define our sets. We have P, which is our set of individuals, the sheep, and L, which is our finite set of available safe locations. Our task is to map elements from P to L. However, we might not use every single safe location available. We need to select a specific subset. We define S as the subset of locations that are actually used. Effectively, we are looking for a function f that assigns every sheep to a location in S. So what defines a good distribution? We are looking for a mapping that satisfies specific conditions. We want to maximize the separation between those chosen locations. So for every pair of distinct sheep assigned to locations, the distance between them must be respected. And of course, we want for our set to be minimal. This brings us to our objective function. We assume we have a distance matrix D representing the distance between any 2 locations. Our goal is the max-min dispersion problem. So we want to choose a subset S of size k such that we maximize the minimum distance between any 2 selected locations. So in simple terms, we want the sheep to be as far apart from each other as possible within the chosen set. The result of this optimization gives us S star, so the optimal set of locations, and D star, the best possible safety margin. Still, how do we solve this? Well, our smart sheep will use MILP, mixed integer linear programming. This allows her to make discrete choices like yes or no, while optimizing a continuous value, so our distance. We introduce binary decision variables xy. If xy equals 1, it means location I is selected, so it is a part of set S. If it's equal to 0, the location is ignored. We also add the constraint that the sum of all x must equal k, but it's just to ensure we pick exactly the required number of locations. Now, here's the challenge. We want to say if location I and location j are both selected, then the global minimum distance D must be at most the distance between them. But standard solvers cannot understand if-then statements directly. So we use the big M linearization technique shown here. We transform the logic from before into this inequality. Basically how it works is that when both locations are selected, so they both equal 1, the term on the right becomes 0, and the constraint D is less or equal than the distance becomes active. If either location is not selected, the term becomes large, thanks to the big M, making the constraint irrelevant. The big M is usually the biggest distance. Now, let's move to a visual example to see how this works in practice. We define our specific safe locations on the coordinate map. Here's how they look on our map. Still, I would like to emphasize here that this is only about distance. The sheep goes to the location that is the closest to them and is not full at capacity. In this example, capacity is 3 because we have 9 sheep. So our primary goal right now is to pick the locations. We need to select exactly 3 out of these 4 spots. And the challenge is to find the specific trio that keeps the location as far apart from each other as possible. Then the assignments of sheep will naturally follow once we have established this safe geometry. The first step to the solution is generating the full distance matrix. This table shows the distance between every possible pair of locations. So for example, the distance between location 1 and location 2 is 50 meters. Now, here we see the logic laid out quite clearly. We listed every possible combination of these 3 locations, and for each group we identified the weakest link, so the shortest distance between any 2 points in that group. As you can see, 3 of the 4 options result in a safety distance of only 41. And so these are suboptimal and there is our only winner, the combination of locations 1, 2, and 4. This gives us a safety margin of 50 meters. So here is our final optimal solution. D star is equal 50 meters, and S star consists of location 1, location 2, and location 4. And the graph on the right shows this. The orange dashed line represents the critical 50-meter safety margin. Also, please note that the location 3 is left unused because it was too close to the others. And finally, we have a result. A happy, safely distributed flock that's full of happy sheep. So to summarize at the end, we basically converted a logical problem into a linear mathematical model using MILP and Big M. Thank you for your attention. Here are the references.